Hi guys, this is question number 2 in your first review homework paper, and let's get started. So in part A, basically how to solve moment of inertia of an object or of any object using integral. So moment of inertia is basically defined as r squared dm. What does that mean? Let's say you have, so let's go over our question. So you have a triangular object. So they define this first point as 0 and then the last point of this guy as L. So total length of this triangle in the bottom part is like length L. And it also has a lambda, and lambda is like density, all right, because it's then a uniform thing. It's basically increasing. It's going to have more and more mass as you go from this x position to this final bottom, like this position. So you're going to have more and more length as you go over, so you're going to have more and more mass per length, and that's the meaning of lambda. It's like density. So if you think about density, it's mass per volume, and lambda is going to be mass per length. So it is defined as mass per length, but if you would like to consider that calculus way, then you can say that tiny mass dm is going to have, or tiny distance x is going to have tiny mass of dm. So what does that mean? For example, you cut this portion of this. So dm over dx means that in that tiny thickness dx part, you are going to have some mass over here, and this mass is going to be known as dm. So tiny thickness dx is going to have tiny mass of dm, and that ratio dm over dx is going to be lambda. That is the definition of lambda, and this lambda for our question is given as 2m over L squared times x. And in our question, we are trying to figure out the eye of this triangular shape. And the equation, you are going to have that equation in your equation sheet. R squared over r squared dm, an integral of that function. So r here is also length, and it simply measures from the axis of rotation and radius. So in our function, this is defined as x, because I start from 0 and I change my x, or I change my length, and that is given a function as x. So in my equation, that is actually I equals x squared dm. So, but what is the relationship in between dm and x squared? So I know that as x changes, my mass changes, but I don't have a direct relationship with that. But what do I have? I have this relationship. So dm over dx from lambda, dm over dx must be equal lambda, and lambda is given to me. So what can I do? I can just isolate this dm in this equation and replace it. So if you do the cross multiplication, dm will be equal to 2m over L squared times x times dx. So all I do is just take this dx up here. So my dm is 2m over L squared times x dx. So all I need to do now is just replace this dm into that integral, and the rest will be easy to do. So let's go from I x x squared times dm. So I'm going to replace this dm because I don't have x as a function of m, but I have dm as a function of dx. So if I replace it, then I'm going to have an integral that I can solve. So 2m divided by L squared x dx. So that was my dm. So I just replace dm. So now I have a variable x and I have dx. So that means I can solve that integral. And this m and L, these are my final m, total mass of the triangle, and length L is the total length of that triangle, the base of the triangle. So they are technically constant. So my variable is x, and this variable is, what's the boundaries again? I'm going to start from 0 location, and I'm going to go up to L location. So I'm going to go from 0 to L. So you should be comfortable solving that integral right now because you have just the power of x in that equation. So let's rewrite this. So 2m over L squared, that can come out because that's just a constant. So 2m over L squared, and I'm going to have an integral of 0, changing from 0 to L, x squared times x and dx. So x cubed dx. So then what will be my integral? How am I going to find the integral? Take the integral of that x cubed. So 2m over L squared is going to stay as constant outside, so x cubed. So all you do is increase the power by 1, x to the power of 4th, and then you divide it with the power divided by 4, and then you're going to evaluate it from 0 to L, and then close the parenthesis. And if you continue over here, so what are you going to have? Again, 2m over L squared is going to be outside. Open the parenthesis. So what is the rule again? This is the integral, but I have boundaries, so I'm going to replace my variable with the upper boundary minus replace it with the lower boundary. So my upper boundary is L to the power of 4 divided by 4. This is me replacing the upper boundary minus replace this variable with the lower boundary, 0 to the 4th divided by 4. So 0 times 0 times 0 times 0 is 0. 0 divided by 4 is again 0. So you have nothing over here. So my equation is basically 2m over L squared times 4 L to the power of 4 divided by 4. So now all I need to do is cancel out the same values. So L squared will be, so you basically have 4 L's there, but you have 2 right here, so it's going to bring it down to 2. You have 2 here, 4 here, so that's going to cancel out 2. So as a result, my moment of inertia for that triangle is going to become mL squared divided by just 2. And that's what they wanted you to do. They wanted to show you that in part B, they are asking for basically total moment of inertia of the new shape. So what do they have as a new? So they had this disc, this hoop, and then that had a moment of inertia of mL squared already. And then what did they do? They have put it 3 of those triangles together from the center. So then I already measured the moment of inertia of one of them from the center, and then that was mL squared over 2. So what's the total moment of inertia of this? To find a total moment of inertia, you just need to add all of those 4 together. So you have 3 of the bars, and then or rods actually. So 3 of the rods plus 1 of the hoop. So if you add basically the moment inertia of all of those, you will basically find the total moment inertia of the system. So 3 times ml squared over 2 plus ml squared. So if you think about it, 3 over 2 is 1.5 plus another 1, 2.5 ml squared. So your I total will be equal to 5 ml squared divided by 2. So it's again 2.5 or 5 over 2 ml squared. And that is the total moment of inertia of my system. In part C, they are asking for the angular velocity of that disk. But what is happening to the disk? You have this disk, and then they are basically applying some force on it over a certain period of time. So, and they do that tangentially. So they basically apply some force over a period of time, delta t, and this is able to rotate from the center, so it's not going anywhere, it's just spinning around itself, but you are applying a force from the edge of that disk, and then the question is, what will be the final omega? What will be the final velocity of that disk? And they tell you that it starts from rest, meaning that your initial angular velocity is 0 radian per second. So you start from 0 and they're asking for what's the final of it. And they give you the force as F and they give you time as delta T. So again, you need to think about what can bring those, like all of the 3 variables together. So you have initial final omega, you have force, and you have time. So you should think about the rotational version of impulse. And if you think about it, it was torque delta T equals change in angular momentum. And that's basically I times change in omega. So torque, if you remember, is going to be force times distance from the axis of rotation. So my force is given, so it is F. And what was a way for us to figure out the torque or the lever arm? So you basically draw the line over the force, and then you were trying to figure out the perpendicular distance of that force from the axis of rotation. So what is this length from the axis of rotation from the force? That was given as, remember, L, not R. So my torque will be basically the force that was given to me times the lever arm, which is L, times delta T. And I is, which I are we talking about? We are rotating all of the 3 objects, so we are talking about the total omega moment of inertia of the system. So it is basically 5 ml squared divided by 2 times delta omega. It's final minus initial, so final is the unknown and initial is 0. So that is going to get basically going to be just omega final. And that's what I'm going to try to figure out. And I am able to use F, L, delta T, and M. So I can use all of the variables in that equation. So all I need to do is just solve this for V final, or omega final. So take this 2 up there, and then take this 5 ml squared to the bottom, and that's the equation, and that's the final answer for that question. So 2 goes up there, 2 F L delta T, and you divide it with 5mL squared, 5mL squared. So that is my final. Part DI, so it has two parts. So this time you're going to have the disk, and then it's going to go up on the ramp, and they're asking for free body diagram of that disk again. So let's draw this like this. So if it's going up, let's see what the free body diagram is. You always think about the forces that is acting on the object. So you always think about the first one as gravity, because gravity always acts on the objects that is moving on Earth, and this is going to be straight downward, Fg. And you have a surface is requiring a normal force or reaction force, and we call it normal force. And for this disk to be able to go up, it is going to need a friction, because without friction it wouldn't be able to go up. It would be just like spinning on the same location. You wouldn't be able to go up. We need to think about the direction of friction. So we always say that the friction is going to be against movement. So we are going up, so it might seem like the friction is going to go down. However, once you think about the motion over here, so for rotational stuff, it's going to be a little bit different. So it's like walking. So this guy is going to be rotating in this direction. So to be able to go up, it is basically, this is the surface, so it is going to basically push on the surface backwards. So it is, once it's sliding, rotating, it's basically creating a force going in this direction. If it rotates, think about it, it rotates in this direction. So it is pushing in that direction on the surface. But this is the force acting on the surface. But what are we looking at? We are looking at the forces on the disk. So Newton's third law requires action, reaction. So once you are rotating like this, you basically push the surface on the left. That means the surface is going to act on the disk up. Alright? So friction force will be going up on the disk. So DII is asking for your explanations of your forces in your free body diagram. So Fg by is gravity, or Fg is gravity. It is always straight down. Fn is the reaction force of surface. It is always perpendicular to the object, to the surface. So friction force is basically going up. So what's the best way of describing that? Friction force is downward reaction pair of downward push of the disk when it rotates. So I don't have space over here, but since it's reaction pair is going to be opposite of this down force. So part E. So what would be the height that is going to go up to? Well, simply what we do is use conservation of energy. So initially, it is going to have some energy, and the maximum height that it can go up to is basically this h that we don't know. And the question is basically asking for what is the height difference of the center. So they are simply asking for that distance. So all we need to figure out, equalize your initial energy to your final energy. And at the end, all we have is, since they're asking for the maximum height, meaning it's going to go all the way up and it's going to stop, then it's going to roll down. So that means all the way up it has no kinetic energy. All of the energy that it has is potential energy. And at the bottom of the surface, it has no potential energy. All it has is kinetic energy. So all we need to do is just combine or equalize this initial kinetic energy to the final final potential energy. But there is a little bit difference here because this is a rolling object. So it's going to have both rotational kinetic energy and transitional kinetic energy, and that's supposed to be equal to gravitational potential energy. Alright, so that is the important part. You need to recognize that it's rotating, it's not just going straight. So then, what is a way to find that? Rotational version of kinetic energy is 1/2. Instead of mv squared, instead of m, we're going to use moment of inertia, times, instead of v, we use omega squared, plus we are going to have regular kinetic energy, which is 1/2 mv squared, and then that is going to be equal to the gravitational potential energy, which is mgh. So all we need to do is solve this entire equation for h with the quantities that we are allowed to use. So what are the quantities that we are allowed to use? We can use L, we can use I total, we can use omega, and we can use m. So let's see what we can do. So we can use I directly. So I'll just use I as I. So 1/2 I. And they are talking about total, so I total, because we are talking about the disk. So it's not just momentum inertia of one of pieces, it's the total. And omega, I am able to use my omega as omega, so I'll just use omega squared. So there's no problem with the rotational part, because all the quantities were given in terms of rotational stuff. But now we need to figure out what to do with the linear part. So 1/2. So m, which m are we talking about over here? We are talking about the mass of the disk. So if you remember, mass of one triangle was already given as m in the first part, so I have 3 of them. So it is basically 3m from those 3 discs, like 3 rods. And I also have the hoop itself. So in total, I have 4m, actually, 4 capital M. So now, what is the V in terms of omega? If you think about it, as you go farther away from the center, you're going to have faster and faster speed, but that's a linear one. So that means as that V is going to be related with R, and as R increases, you're going to have more V. So that means it is R, which is radius, times omega. And what's my R in this scenario? So distance from my center to the edge of the circle is basically length L. So L times omega, which is the angular velocity of my disk. is equal to mgh. So I'll just write this down over here because I don't have space right there. So what is the mass again? Which mass are we talking about? We are talking about all of them, which is 4mg. The h is the unknown, so that's h unknown. I'm not sure if it's given as capital H, but it's fine. So we are trying to solve this for basically h. Well, you have it squared right here. So now let's rewrite this equation and see what we have. 1/2 I total omega squared. There's nothing to do over here. So 1/2 4m. Let's keep 1/2 because I have 1/2 over here. So that might be easy for me to do the math later on. So 4m L omega squared is going to be basically L squared omega squared, and that's equal to 4mg times h. So I have 1/2, 1/2. I have omega squared. So I can take this part into omega squared over 2 parentheses. And then if you remove omega squared over 2 from this, you will only have I total plus, and if you remove 1/2 omega squared, you're going to have 4m L squared on this side. And that's equal to 4mg times h. So the last thing that we're going to do is basically, there's nothing that you can do over here. It's just a bunch of variables. You just divide everything with 4mg, and then that cancels out. And if you divide this side with 4mg as well, your final h will be, that is a division as well. So omega squared over 4mg and 2, so that's going to be 8mg, and then I total plus 4m L squared. I know this is a stupid solution, but this is the answer.